I don't know what happened to the recording I made during the session, but apparently it's all blank. So I'm going to try again. For this lab, you are supposed to use Verilog to make a multiplexer to implement a function. And so your lab gives you two functions. Let's find them. So the functions are S of A, B, C, D equals the sum of those minterms, or T of A, B, C, D equals the sum of those minterms. And you're supposed to design a circuit to implement the following. And it says, see section 4.11 of the textbook for some examples. So these are the ones you're supposed to do. So I'm going to do this in three parts. The first part is going to show how you can use a multiplexer to implement a function just in general, whether you have Verilog or not. The second part is going to be how to use two multiplexers to make a larger multiplexer, and then the third part is going to be about how to do the Verilog. So we're going to start with how to use a multiplexer to implement a function. So I'm not going to do this function, but let's do a similar function. So let's say I had S of A, B, C, D equal the sum of the minterms 4, 5, 6, 12, 14, and T of A, B, C, D is the sum of the minterms 1, 2, 3, 7, 11, 13, 14. All right. Let's start off by saying that we had a 0 to 15 multiplexer. So we would take A as written here. A is the most significant bit. So A, B, C, D, if I want that to equal 4, be 0, 1, 0, 0. That's 4. 5 would be 0, 1, 0, 1. 6 would be 0, 1, 1, 0. 12 would be 1, 1, 0, 0. And 14 would be 1, 1, 1, 0. So 4 has A equal to 0, B equal to 1, C equal to 0, and D equal to 0. And 5 has A equal to 0, B equal to 1, C equal to 1, and D equal to 1. So it's like that. So A, B, C, and D are your select inputs. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So this is a 16-to-1 mux. So I have 16 inputs and 1 output. Well, 16 on this side, and then I also have the 4 select. And so if I wanted to implement function S, then I would put a 1 onto 4, 5, 6, 12, and 14. So that would be function S, and that's how you would do it. And if I wanted function T, I'd put a 1 onto all of those. And then this output, so if this was function S, this would be my output, S. A, B, C, D would be my selects, and I would have 1 for each of these and 0 for the others. If I wanted T, I'd put a 1 on each of those. Okay, so that's part 1. That's how you do a multiplexer. Well, how do you do this if you have 2 multiplexers? I did this one way in the lab, but I think I'm going to do it another way that you'll like better. So what if you only have a 0 to 8 multiplexer? 0, 1, 2, 3, 4, 5, 6, 7, 8. How can you make a 0 to 15 multiplexer out of 2 0 to 8 multiplexers? Well, what you would do would be you would have your input A, B, C, and D, and you would have B, C, and D be your select inputs. Sorry, that's so messy. But I have B, C, and D being my select inputs. And if you think about the numbers from 0 to 15, those are the numbers from 0 to 7. And those are the numbers from 8 to 15. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. And this is A, B, C, D, and A, B, C, D. Now look at B, C, and D. B, C, and D are the same on both of these columns. 0, 0, 0, 0, 0, 0. 0, 0, 1, 0, 0, 1. So B, C, and D are the same on both of them. What's different is A. So we can string together 2 0 to 7 multiplexers. And did I put 8 on these? I put 8 on this one. I do that all the time. We can string together two 0 to 7 multiplexers by choosing between the two with 8. So, with A. So if A is 0, then we want the first multiplexer, and if A is 1, we want the second multiplexer. So how do you make that work? So if I want to get the numbers from 0 to 7, then I'll use the output from this first multiplexer, and I will AND that with not A. So if A is 1, then my output here is always going to be 0. If A is 0, then my output will correspond to whatever my input is on this first multiplexer. So if A is 0, what this does is it gets the value from this multiplexer if A is 0. And if A is 1, it just gives you 0. And then we will AND the output of this multiplexer with A. So what that does is if A is 1, then we get the value from this multiplexer, and if A is 0, then this value is 0. So we now have made a 0 to 16 multiplexer. Alright, now how are we going to do this in Verilog? Okay, so your book shows the code using a case statement for making a 4 to 1 multiplexer, and you are supposed to make an 8 to 1 multiplexer. So we will just model it off of this. Alright, so let us code this. Our inputs are going to be A, B, C, D, and our outputs are going to be S and T. But I'm not ready to do my main module yet. I need to make the multiplexer. So I've copied this code from the book, and I'm going to make it an 8-to-1 multiplexer. And I like to have my most significant bit first, and so W is going to be my 8 bits from 7 to 0, and S is going to be my select, that's interesting. Okay, so I'll do 7 to 0, and S is going to be my select, and it's going to have 3, because it's got to be 3 bits, so 2 to 0, and I'll have F be my output. And the way this works is it just uses a case statement, and so the case statement just selects the value that based on your control input. So based on what S is, so S is this 3-bit number, based on what S is, then that is going to tell you what your output is going to be. So all I need to add here are corresponding entries for the values from 4 to 7. So what W is W is the input for your multiplexer. So if you look at your multiplexer and it has from 0 to 7, W has the values that you would have on this multiplexer. So if you had the values 1, 0, 1, 1, 0, 1, 1, that's 7, 1, 2, 3, 4, 5, 6, 7. Then your W from 7 to 0 would equal whatever you have on the 7. So it would be 8, an 8-bit binary number starting from the bottom, 0, 1, 1, 0, 1, 1, 0, 1, because I have my most significant bit first. And then what the multiplexer does is, let's say your select is the binary number 0, 1, 1, which is 3. Then your function is going to have the value, so this is 7, 6, 5, 4, 3, 2, 1, 0. If this is your control, then you have 3, and your answer, 0, 1, 2, 3, is going to be 1, because W of 3 equals 1. Okay, so now let us so we've made an 8-to-1 multiplexer. Let's make a 16-to-1 multiplexer. So this is a little different from what we did in the session. give them different names just to keep it different. Call that Y. And I'll call that C. And I'll call that G. Okay, so now we want to instantiate two of our 8-to-1 multiplexers. So I will say, what did I call it? Mux 8-to-1. I'll call it low. And if I look at Mux 8-to-1, my inputs are W, S, and F. So I want low to take the values from 7 to 0 of Y. And 2 to 0 of C. And my output, I'll call it, it's going to need to be a wire. I'll have ML and MH for multiplexer low and multiplexer high. So ML Okay, so I took the bits from 0 to 7 and I put them in the low multiplexer, and the bits from 8 to 15 and I put them in the high multiplexer. So what I just did was I made this one is my low and this one is my high. So I need to AND this together with the first bit of the control knotted, and for the second one with the first bit not knotted. So I now need to make, I'll do assign G equals not C3 and ML or C3 and M high. So now I'm in the situation that I started with. I now have a 16:1 multiplexer. So now that makes this bit of code very easy. So mux 16:1 function S, and then I would give it my 16-bit number that had the values that I wanted. So I had 4, 5, 6, 12, 14, so that would be so bit 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So I would make the fourth bit 1, the fifth bit 1, the sixth bit 1, and 12 and 14, and everything else 0. I skipped 13, 11, 12, no, there's 13. 11, 12, 13, 14, 15. So my number is 0, 1, 0, 1, 0, 1, 0, 1, and then 5 zeros. 3 ones and 4 zeros. Comma, and then my input is going to be putting together A, B, C, and D as a 4-bit number, and my output is going to be S. And then I'll do the same thing for T. number for T. I want 0, 1, 2, 3, 7, 11, 13, 14. So 0, 1, 2, 3, 7, 11, 13, 14, 15. So 0, 1, 1, 0, 1. Got an extra number there. 0, 0, 1, 0, 1. 0, 0, 0, 1, 1, 0, 1. 3 zeros. Missing one on that one. Need an extra 0 there. Alright, and that should do it. So then for the constraints, you need to use the switches and LEDs that they say to use in the lab, which I believe were switches 10, 11, 12, and 13 for A, B, C, and D. And I don't remember which LEDs. Let's see. LED 14 and 15. And I will uncomment these. Now, by the way, there are lots of ways to do this. So I showed one way in the session today. I've done it a different way every year that this lab has come up. So you should experiment and play around, come up with your own way of doing it. This is the way that right now I thought would make the most sense, so it's what I did. So that one will be A. So this is going to make, because this is what the lab handout says to do, but this means that your switches are going to be in backwards order in terms of what the binary number looks like. A is the farthest to the right, and D is the farthest to the left. So what does that mean? So on your basis board, you have the switches wherever they are, 10, 11, 12, 13. And this is A, B, C, D. And our function was A, B, C, D was the sum of the min terms, whatever it was. So 2, 3, 5, whatever. So let's say you had to, you wanted to put in the number 5. Well, the number 5 in binary would be 0, 1, 0, 1, A, B, C, D. So that means your switches would be 0, 1, 0, 1. So this order is the reverse of that order. So our elaborated design, I didn't implement T. Let's see, what did I do? Oh, I made both of these S. That's why it looks like that. This one should be T. So each of my functions has a high and a low, and the high and the low are 8-to-1 multiplexers. Okay, well, I was going to do the decoder and also show a test bench, but I really have to get some sleep, so I'll do that early in the morning.